ready to get fired up. Today's deep dive. Well, we're throwing some light on a force of nature we think we know, fire. You might be thinking, okay, I've got fire safety covered, stop, drop, and roll, right?
Right.
But we're going way beyond the basics today.
Yeah.
We're going to explore the surprising science behind how different fires actually burn.
Yeah.
And why those nuances really matter.
What's so fascinating about fire is that it's like such a fundamental part of our world, yet we often just take it for granted, you know?
Totally.
We see these dramatic images of wildfires or burning buildings, but very few of us really understand what's happening at a deeper level.
Exactly. It's like we see the flames, feel the heat,
Yeah.
but don't always grasp like the how and the why behind it all.
Yeah.
Like everyone's heard of the fire triangle, right?
Right.
Fuel, oxygen, ignition.
The classic.
But trust me, there's a whole universe hidden within each of those elements.
Absolutely. And that's where this deep dive comes in. When you understand those details, the different types of fuels, the crucial role of oxygen, you know, how heat dances around, that's when you truly unlock the secrets of fire. And when you unlock the secrets of fire, you empower yourself with knowledge. You empower yourself with safety.
Okay, so let's unpack this fire triangle a bit. Our source materials talk about different classifications of fires. Why does that even matter?
Yeah.
Shouldn't putting out a fire be as simple as, well, dousing it with whatever's handy?
Not quite. It's like thinking a wrench can fix any problem in your house.
Right.
Just like a plumber needs different tools for different pipes, fighting fires effectively depends on knowing what kind of fire you're dealing with.
So it's more nuanced than just, there's a fire, put it out.
Exactly. We actually have two main classification systems.
Yeah.
The NFPA, which is used in the US, and then there's another one that's used in Europe. And they both categorize fires based on what's burning, but there are key differences that highlight just how much the fuel really matters.
Give us an example. How different can these fires really be?
Think about a sizzling pan of oil catching fire in your kitchen.
Okay.
A common enough mishap.
Right. Happens all the time.
The NFPA system actually has a separate class just for cooking oils and fats, recognizing how dangerous they can be.
Oh, wow. I never even realized that. But isn't it just, a kitchen fire?
That's what's so tricky. It's easy to underestimate them. But imagine tossing a cup of water onto that grease fire. You're not putting it out. You're creating a volatile explosion of steam and scattering burning oil everywhere.
Yikes. That's definitely not the outcome I'm going for.
Exactly. And that's why understanding these classes is crucial. That grease fire requires a specific type of extinguisher, one that can smother the flames and cut off the oxygen supply. It highlights how the fuel part of the fire triangle, it isn't one size fits all.
So the type of fuel dictates how you fight the fire. What about those other two sides of the triangle? Oxygen and ignition. What's so important about those?
Let's dig a little deeper into the oxygen side by talking about the combustion process itself.
Okay, time for a chemistry refresher.
Well, think of it like building with Legos.
Okay.
You have your fuel, which is like a pile of Lego bricks full of potential energy. Then you have oxygen, those vital connecting studs that hold everything together and release that energy.
So oxygen acts as a sort of dot trigger for the fuel to release its energy.
Exactly. In a perfect world, you have complete combustion where all the fuel combines with oxygen, releasing energy neatly as heat and light, leaving you with just carbon dioxide and water as byproducts. It's like building a grand Lego castle without a single brick out of place.
But things don't always go according to plan, do they? What about those times when there isn't enough oxygen present?
That's where we get incomplete combustion. And that's where things get messy and, frankly, dangerous. Going back to our Lego analogy, imagine trying to build that castle, but you're short on connecting studs. You might manage to cobble something together, but it'll be unstable, wonky, and prone to collapse.
And I'm guessing this unstable Lego structure translates to dangerous byproducts in a fire.
Precisely. Instead of neatly producing carbon dioxide and water, incomplete combustion can create a cocktail of nasty byproducts, including carbon monoxide.
Carbon monoxide being the infamous silent killer we always hear about.
Exactly. It's a colorless, odorless gas that can quickly incapacitate you on a fire. You can't see it, you can't smell it, and that's what makes it so incredibly dangerous.
That's a chilling reminder that there's more to fire than meets the eye.
Absolutely.
We've got these invisible threats lurking within the smoke, not just the flames themselves.
All right.
Okay, so we talked about the fuel, we talked about the oxygen. What about that third crucial side of the fire triangle, the ignition?
So with ignition, well, instead of just talking about how fires start, let's talk about how that heat behaves once a fire is going.
Okay, so how does heat actually travel in a fire? Does it just like radiate outwards from the flames?
It's more dynamic than that. Heat loves to travel, and it has three main ways of doing so: conduction, convection, and radiation.
Okay, I'm intrigued. Break those down for us. What's conduction?
Imagine you're holding a metal rod over a campfire.
Okay.
The end you're holding is cold at first, but as the heat from the fire travels up the rod, it gets hotter and hotter. That, my friend, is conduction heat transfer through direct contact.
Okay. I get it. What about convection?
Yeah.
I feel like I remember that word from high school science class, but my memory's a little hazy.
Convection is all about heat transfer through the movement of fluids. Think air or water. Imagine a hot air balloon. The burner heats the air inside the balloon, making it less dense and causing it to rise. That, in essence, is convection.
So in a fire, the hot air and gases rise, and they carry that heat with them.
Exactly. And as those hot gases rise, they can preheat materials above them, sometimes to the point of ignition. It's why fire can spread upwards so rapidly, even jumping across gaps.
Wow. It's like a chain reaction of heat. So what about that third method of heat transfer, radiation?
Radiation is the sneaky one, traveling as invisible waves of energy. Think about how you can feel the warmth of the sun on your face, even though you're not touching it.
Okay, that makes sense. But how does that apply to a fire?
Think of a roaring bonfire. Even if you're standing a safe distance away, you can feel the intense heat radiating outwards. That heat is traveling as electromagnetic waves, just like light.
Wow. So even without direct contact, the heat from a fire can still ignite nearby objects through radiation.
Precisely. And that's why understanding these three methods of heat transfer, conduction, convection, and radiation is crucial for understanding how fires behave and spread. But it gets even more interesting when we start talking about a phenomenon called flashover.
Flashover. That sounds intense. What is that?
Imagine you're a firefighter entering a burning room. The fire might seem somewhat contained at first, but here's the thing about convection. As hot gases rise and heat up the entire room, they also heat up every object in that room. Furniture, carpets, even the air itself.
Yeah.
Now imagine a point where the temperature gets so high that everything in that room reaches its ignition point simultaneously.
Wait, so the whole room bursts into flames at once?
Yeah.
That's terrifying.
It's called flashover, and it's one of the most dangerous situations a firefighter can encounter. It happens incredibly fast.
Wow.
And that's why understanding how heat behaves is so critical.
Right.
But speaking of rapid fire spread, sometimes that energy release happens even faster, and that's where we get explosions.
Explosions. Okay. Now we're getting serious. Tell us more about those.
So explosions are essentially fire on fast forward, a sudden, intense release of energy that creates this powerful pressure wave.
So instead of a slow and steady burn, we're talking about like a near instantaneous burst of energy.
Exactly. Think of it like this. If fire is a simmering pot, an explosion is like popping a champagne cork. All that pent-up energy is released in a fraction of a second. And just like a champagne cork can launch itself across a room, an explosion creates this powerful shockwave that can cause significant damage.
Okay, that paints quite a vivid picture. What causes that sudden, intense energy release in an explosion?
There are a few different scenarios, but a common one involves the ignition of a flammable gas or vapor cloud. Remember those hydrocarbon molecules we talked about earlier, the ones that make up fuels?
Yeah.
Well, when those molecules are in a gaseous state, they mix with air, and that creates a potentially explosive mixture.
So if there's like a gas leak in a home, for example, and it mixes with the air, that could create the right conditions for an explosion if it finds an ignition source.
Exactly. It's like creating this giant invisible powder keg in the air, and all it takes is a spark,
Right?
a faulty appliance, a lit cigarette,
Oh, wow.
to set it off.
That's scary to think about.
Yeah.
Are there other ways that explosions can occur?
Absolutely. Another way is through the rapid heating of a confined liquid. Think about what happens when you heat a closed container of water on a stove. The water turns to steam. And because steam takes up more space than water, the pressure inside the container builds.
And if that pressure gets too high, boom, the container explodes.
Precisely. The same principle applies to other liquids, but when those liquids are flammable, the results can be far more dramatic.
So we've got these invisible gas clouds and rapidly heated liquids, all potential recipes for disaster if they're not handled carefully.
Exactly. And understanding how those explosions behave is crucial for mitigating their risks. That's where a concept called overpressure comes into play.
Overpressure. That sounds like something out of a superhero movie.
Well, it's actually a real-world concept that helps us understand the destructive power of an explosion. It's basically the amount of pressure above normal atmospheric pressure that's created by the blast wave.
So it's like a sudden spike in pressure that radiates outwards from the explosion.
Precisely. And to visualize this, imagine a series of concentric circles drawn around the point of the explosion. Those circles represent different levels of overpressure, with the highest pressure closest to the center decreasing as you move outwards. Kind of like a bullseye.
So the closer you are to the bullseye, the stronger the blast wave.
Yeah.
That makes sense. But how is this overpressure concept used in the real world?
It's incredibly valuable for things like emergency planning and determining safe distances during like an industrial accident, for example. By understanding the overpressure circles, first responders can quickly establish evacuation zones, ensuring people are a safe distance away from the blast. It helps them assess the potential damage to buildings and infrastructure as well.
So it's not just about understanding what causes explosions, but also how their impact spreads outwards. It seems like knowing the why behind these concepts can be crucial for safety in so many different contexts.
Absolutely. It's all about being prepared, understanding the risks, and taking appropriate precautions.
It's about understanding that fire safety isn't a one-time lesson. It's an ongoing conversation, a constantly evolving field of knowledge.
Well said, and that's what makes this deep dive so crucial. By understanding the science of fire, recognizing its awesome power, and respecting its potential dangers, we can all become more informed and empowered individuals.
Well, there you have it. A blazing journey through the fascinating world of fire. From the fundamentals of the fire triangle to the complexities of combustion chemistry, the dangers of flashover, and the growing threat of wildfires and a changing climate, we've covered a lot of ground today.
It's been a pleasure diving into these fiery topics with, you remember, knowledge is the best fire extinguisher.
So true. Stay safe out there, everyone, and keep those curious minds burning bright.